Picture this. While politicians debate carbon emissions and news anchors breathlessly report on melting glaciers, something far more unsettling unfolds in a realm we've barely explored. Down below, past the sunlit surface where whales breach and surfers ride waves, past the twilight zone where light fades to memory, lies the deep ocean. A vast, cold, lightless world that covers more than half our planet. For millions of years, this abyss remained Earth's most stable environment, a frozen-in-time sanctuary where temperature barely fluctuated and ancient rhythms persisted undisturbed. Scientists once believed these depths were immune to our surface chaos, protected by sheer distance and the crushing weight of kilometers of water. Yet recent discoveries paint a different, darker picture. The deep ocean is transforming, and it's happening faster than anyone predicted. What we're witnessing isn't just change. It's an invisible apocalypse unfolding in absolute darkness. And here's the truly unsettling part. We've explored less than 5% of this realm, meaning whatever is happening down there, we're seeing only glimpses of a much larger horror story. Think about the word stable for a moment. In the deep sea, stable meant temperature variations of less than 1 degree across centuries, oxygen levels that remained constant for eons, and salinity that never shifted. These weren't just numbers on a chart. They were the foundation of life in an environment more hostile than outer space. Creatures evolved over millions of years to exist in this unchanging cold darkness, their bodies perfectly calibrated to survive where pressure can crush submarines like tin cans. But what happens when stability itself becomes unstable? Recent studies reveal that up to 40% of the ocean's upper 1,000 meters have undergone significant shifts in at least 2 critical properties compared to 6 decades ago. Some areas show simultaneous changes in temperature, salinity, and oxygen, 3 variables that should never change together in a healthy ocean. It's like someone rewrote the laws of physics down there. The deep ocean, once Earth's great constant, is entering uncharted territory, and the creatures that call it home have nowhere to run. Here's where things get genuinely eerie. Scientists have coined a term for what's happening: compound state change. Sounds clinical, almost boring, until you understand what it means. Imagine living in a house where the temperature suddenly spikes 10 degrees. The air becomes harder to breathe, and the water from your tap tastes completely different. All at once, with no warning. That's what's happening to deep-sea ecosystems right now, except these creatures have no concept of climate change, no ability to understand why their ancient world is betraying them. The most intense transformations are occurring in the tropical and subtropical Atlantic, the North Pacific, the Arabian Sea, and the Mediterranean, regions that should be teeming with life but are instead becoming biological danger zones. Even more disturbing, these changes are penetrating deeper than scientists thought possible, reaching into what was once considered the stable heart of the ocean. The abyss itself is warming, acidifying, and losing oxygen simultaneously. How do you adapt to that when your species took millions of years to perfect survival in the old world? But wait, let's pause and consider something that should make your skin crawl. The deep ocean absorbs 90% of the excess heat trapped by greenhouse gases. That's right. While we feel warm summers and mild winters at the surface, the true thermal burden of climate change is being swallowed by the depths, stored in waters that may not surface again for centuries. This isn't a temporary buffer. It's a debt being written in an account we can't easily access. Recent research confirms that even if we stopped all carbon emissions today, deep-water warming would continue for decades, possibly centuries. The heat is already there, working its way down through layers of water like poison seeping through soil. And here's the question that should haunt us. What happens when that heat reaches the seafloor? What ancient things might it awaken? What stable systems might it destabilize? The ocean isn't just absorbing heat. It's incubating the consequences of our actions in a pressure cooker we can't open. Now imagine you're a creature of the abyss. Perhaps a giant isopod the size of a football, or an anglerfish with teeth like needles and a bioluminescent lure dangling before its face. Your ancestors have lived in the same narrow temperature range for millions of years, your metabolism tuned to waters hovering just above freezing. Then, gradually but relentlessly, your home starts warming. Not by much, maybe 1 or 2 degrees over a few decades, but in the deep sea, that's apocalyptic. You have 2 choices. adapt or migrate. Adaptation isn't really an option when change happens this fast. Evolution works on geological timescales, not human ones. So you migrate, following the cold water toward the poles like a refugee fleeing disaster. But here's the nightmare. You're not alone. Thousands of species are making the same desperate journey, and they're doing it in complete darkness, guided only by instinct. Scientists call this climate velocity, the speed at which creatures must move to stay within their tolerable temperature range. In the deep sea, that velocity is nearly 4 times faster than at the surface. 4 times faster, in an environment where food is scarce and every calorie counts. Can you imagine the chaos unfolding down there right now? And here's where mystery blends with horror in ways that science fiction writers couldn't invent. As these migrations accelerate, ecosystems that have existed in equilibrium for eons are collapsing and reforming in bizarre new configurations. Tropical species are invading polar waters, bringing with them alien behaviors and metabolisms that overwhelm native species. Predator-prey relationships that took millions of years to balance are being scrambled like a deck of cards thrown into the air. We don't know what new ecosystems will emerge from this chaos, but we do know one thing. Up to 95% of deep-sea species in some regions are experiencing irreversible loss of habitat connectivity. They're becoming isolated in shrinking pockets of suitable water, cut off from breeding populations, trapped in biological dead ends. It's like watching islands sink one by one, stranding populations on disappearing mountaintops. The deep ocean is fragmenting into a patchwork of viable and uninhabitable zones, and we're only beginning to map where the boundaries lie. Let's talk about what we don't see, because that might be the most terrifying part of all. Down in the abyss, 90% of creatures produce their own light through bioluminescence. They glow in the darkness, communicating, hunting, mating with living lanterns and chemical fires that burn cold. But lately, scientists have documented something strange. Unexplained bioluminescent displays, mass light shows that seem to have no purpose. Are these creatures panicking, signaling distress, trying to communicate across suddenly fragmented populations? We simply don't know. Some phenomena, like Milky Sea events where vast stretches of ocean glow with steady, eerie light visible from space, are increasing in frequency, possibly triggered by warming waters that favor massive blooms of bioluminescent bacteria. It's beautiful and deeply unsettling. The ocean itself glowing like a ghost, broadcasting a distress signal we can barely interpret. What other signs are we missing? What other changes are unfolding in that 95% we haven't explored? The deep ocean might be screaming, and we're too far away to hear it. So what does all this mean? Not for the anglerfish and isopods and bioluminescent jellyfish, but for us? Here's the uncomfortable truth. The deep ocean isn't just some remote wilderness we can ignore. It's Earth's climate regulator, its carbon storage system, its thermal battery. When compound state changes push these ecosystems beyond their adaptive limits, they stop functioning as they should. The ocean's capacity to absorb carbon weakens. Its ability to regulate heat distribution falters. The consequences ripple upward. Destabilized fisheries, compromised food security for billions of people, more destructive storms, accelerated warming. We're not just passive observers of an ecological tragedy unfolding in the darkness. We're participants in an experiment whose results we cannot predict, conducted on a system we barely understand. And here's the most haunting realization. The deep ocean is the largest ecosystem on Earth. When it transforms, everything transforms. The abyss isn't just changing. It's dragging the rest of the planet with it, 1 degree, 1 dead zone, 1 stranded species at a time. We thought we knew what to expect from the deep sea in the era of global warming. We were catastrophically wrong. Imagine you've lived your entire life in the same neighborhood. Your parents lived there, your grandparents, your ancestors stretching back millions of years. The temperature never changes. The rhythm of life follows patterns so ancient they're written into your DNA. Then one day, the ground beneath your feet starts warming. Not dramatically, just a degree or 2, but in your world, that's the difference between survival and extinction. This is the reality facing deep-sea creatures right now, and their response is something scientists call climate velocity. It's a deceptively simple concept with horrifying implications. How fast must a species move to stay within its tolerable temperature range as the ocean warms? For creatures living beyond 1,000 meters depth, the answer is shocking. They're migrating toward the poles at nearly 4 times the speed of surface animals, fleeing warming waters in what may be the largest mass migration event in Earth's history. And here's the truly unsettling part. They're doing it in complete darkness, navigating an alien landscape they've never encountered, racing against a warming they cannot comprehend. Let's talk numbers, because the scale of this exodus should take your breath away. Scientists analyzed data from 20,000 marine species and discovered something that rewrites our understanding of deep-sea stability. At depths greater than 1,000 meters, creatures are relocating faster than their shallow water cousins, despite living in what should be the most stable environment on the planet. By the end of this century, organisms in the mesopelagic zone, that twilight realm between 200 and 1,000 meters, could be moving 4 to 11 times faster than surface species are migrating today. Think about what that means. These aren't birds that can fly across continents or mammals that can walk thousands of miles. These are creatures adapted to extreme pressure, extreme cold, and extreme scarcity of food. Every movement costs precious calories in an environment where a meal might come once a month. Yet they're migrating at speeds that suggest genuine desperation, driven by changes so fundamental they override every survival instinct except one: escape the heat. But here's where the nightmare truly begins. Not all of them can make it. Up to 95% of deep-sea species in some regions are experiencing irreversible loss of habitat connectivity. Let that sink in for a moment. Habitat connectivity means the ability to reach suitable living areas, to find mates, to maintain genetic diversity across populations. When that breaks down, species become isolated in shrinking islands of tolerable water, cut off from the rest of their kind. It's like a slow-motion apocalypse playing out across the ocean floor. Imagine watching islands sink one by one, stranding populations on disappearing mountaintops with no way to swim to safety. Some creatures find their migration routes blocked by underwater canyons, seamounts, or zones where oxygen has dropped to lethal levels. Others simply can't move fast enough, their metabolism's too slow, their reproductive rates too glacial to keep pace with the warming. They're trapped in waters that are becoming uninhabitable, and there's nowhere left to go. Now consider the compounding horrors these migrants face. It's not just temperature that's shifting, it's everything at once. Scientists call this compound state change, and it's pushing ecosystems beyond any adaptive limits evolution prepared them for. As creatures flee poleward, they encounter waters with different salinity levels, affecting their cellular function and buoyancy. Oxygen concentrations are dropping in many mid-depth zones, creating dead zones where nothing can survive. The very chemistry of seawater is changing as the ocean absorbs carbon dioxide, making it more acidic and dissolving the shells and skeletons of countless species. It's like trying to escape a house fire only to find that the air outside is toxic, the ground is unstable, and the path to safety keeps shifting. Even minor changes in deep water temperature and oxygen gradients can cause dominant species turnover and change entire ecosystem structures. What happens when the foundational species, the plankton, the small fish, the filter feeders, disappear or relocate? The entire food web collapses like a house of cards. Here's a case that should haunt you: the Antarctic Peninsula, where just 0.2 of a degree of warming over 30 years allowed alien red king crabs to invade. These predators, previously kept at bay by the cold, suddenly found themselves able to cross a thermal barrier that had protected Antarctic ecosystems for millions of years. They swarmed onto the continental margin like an invading army, their claws crushing everything in their path: brittle stars, sea cucumbers, delicate filter feeders that had never evolved defenses against such predators. The crabs didn't migrate there by choice. They simply expanded their range as warming waters erased the invisible fence that had contained them. But their arrival transformed the ecosystem completely, wiping out species that had existed nowhere else on Earth. Now multiply that scenario across the entire ocean. How many invasions are happening right now in the darkness? How many ancient ecosystems are being overrun by opportunistic species following the heat? We're witnessing the biological equivalent of borders dissolving, of refugee crises and hostile takeovers happening simultaneously across the largest habitat on the planet. And here's where mystery deepens into something approaching cosmic horror. We don't actually know where most of these migrants are going, or if they'll find suitable habitat when they arrive. The deep ocean remains 95% unexplored. We've mapped more of Mars than we have of our own seafloor. So when scientists say creatures are migrating poleward, what they're really saying is we've detected movement, we've seen population shifts, but the final destinations, the success or failure of these mass migrations, those remain unknown. Computer simulations suggest that many species will run out of habitable water entirely. The poles only extend so far, and polar waters are already occupied by species adapted to those conditions. What happens when tropical deep-sea species arrive in the Arctic and find there's simply no room? No niche, no way to survive. Do they turn back? Do they die out? Or do they transform into something new, something we can't predict? The ocean is conducting an evolutionary experiment at a scale and speed unprecedented in recorded history. Consider the predators following their prey into unknown waters. As smaller species, zooplankton, lanternfish, squid, relocate to cooler depths or higher latitudes, the larger predators that depend on them have no choice but to follow. But this isn't an orderly migration. It's a chaotic scramble where timing means everything. If predators arrive before their prey, they starve. If they arrive too late, the ecological niches are already filled by competitors. Fish that normally hunt at specific depths find their prey has moved up or down, forcing them to venture into pressure zones their bodies weren't designed for. Marine species are already moving toward the poles 6 times faster than land animals, driven by ocean warming that penetrates deeper and deeper with each passing year. The mesopelagic zone, once a stable refuge, is becoming a highway of desperate migrants, all traveling in darkness, all following temperature gradients they can sense but not understand. It's an exodus without a promised land, a journey with no guaranteed destination, unfolding in the largest and least known wilderness on Earth. So what does this great migration mean for the deep ocean itself, and for us who depend on it? Ecosystems that took millions of years to develop are being torn apart in mere decades. Predator-prey relationships are scrambling. Food webs are fragmenting. Biodiversity hotspots around seamounts, hydrothermal vents, and cold-water coral reefs are seeing their residents either disappear or be replaced by invaders with different behaviors and needs. And because we've barely begun to catalog what lives down there, we're losing species we never even knew existed. Some of these creatures might hold biochemical secrets that could revolutionize medicine or biotechnology, but they're vanishing before we can study them. Meanwhile, the ocean's ability to regulate climate is weakening as ecosystems destabilize. Fewer organisms means less carbon sequestration, less nutrient cycling, less resilience against further warming. We're watching a cascade of consequences unfold. Warming drives migration, migration fragments ecosystems, fragmentation reduces biodiversity, reduced biodiversity weakens ocean function, and weakened ocean function accelerates warming. It's a feedback loop spiraling into darkness, happening right now beneath our feet, in waters we cannot see and barely understand. The Great Migration has begun, and there's no turning back. Let's talk about what it takes to survive in hell. Not the fire and brimstone kind, but something far more alien. The abyssal zone, where pressure can crush steel, where no sunlight has penetrated for millions of years, where food drifts down from above like rare snowflakes in a desert. To live there, you need to become something extraordinary, something that would look monstrous to surface dwellers but is actually a masterpiece of evolutionary engineering. Deep-sea creatures have spent eons perfecting adaptations so extreme they border on science fiction. Distensible stomachs that can swallow prey twice their body size. Bioluminescent organs that turn living flesh into lanterns. Metabolism so slow a single meal might sustain them for months. These aren't just interesting features. They're the difference between life and death in the most hostile environment on Earth. But here's the terrifying irony. The very adaptations that make these creatures perfect for their world are now becoming death sentences. Climate change is rewriting the rules of the abyss, and evolution, that patient sculptor that works across millions of years, cannot keep pace with changes happening in mere decades. Consider the anglerfish, perhaps the most iconic monster of the deep. The female anglerfish carries a bioluminescent lure dangling from her forehead like a demonic fishing rod, glowing with bacterial light to attract prey in absolute darkness. Her jaws can unhinge to swallow fish larger than herself, her stomach stretching like a balloon to accommodate meals that might not come again for weeks or months. She moves slowly through the water, conserving every calorie, her body a study in energy efficiency. And then there's the male, tiny, parasitic, fusing permanently to the female's body and dissolving into little more than a sperm-producing appendage. It's horrifying, yes, but also brilliantly adapted to a world where finding a mate in the lightless void is nearly impossible. These adaptations took millions of years to evolve, fine-tuned to waters that stayed within 1 or 2 degrees of freezing. Now imagine those waters warming. The anglerfish's metabolism, calibrated for extreme cold, starts burning through energy reserves faster. Prey species migrate away, following their own temperature preferences. The carefully balanced equation of energy in versus energy out, the foundation of survival in the deep, collapses. What happens to a predator when its hunting strategy fails? Or take the pelican eel, a creature so bizarre it looks like a nightmare dreamed up by a committee. Its enormous mouth comprises roughly 1/3 of its body length, lined with tiny teeth and capable of scooping up small fish and crustaceans like a living net. The pelican eel's body is mostly tail, ending in a complex organ that glows pink. Scientists think it might be a lure or perhaps a warning, or maybe something else entirely because honestly we don't fully understand it. This creature drifts through the mesopelagic zone, waiting patiently for prey to wander within reach of its cavernous jaws. But patience requires stability. The pelican eel's life strategy depends on predictable water temperatures, reliable prey distributions, and specific pressure zones. When compound state changes hit, temperature rising, oxygen dropping, salinity shifting all at once, where does a creature this specialized go? Can't suddenly evolve a different mouth or a faster metabolism. It can't abandon millions of years of evolutionary investment in a single generation. It's trapped between the impossibility of adaptation and the necessity of survival, a living fossil facing extinction in real time. Then there's the phenomenon scientists call abyssal gigantism, the tendency for deep-sea creatures to grow far larger than their shallow water relatives. Giant isopods the size of footballs scuttle across the seafloor, looking like massive armored pill bugs. Japanese spider crabs span over 3 meters from claw to claw. Colossal squid can reach lengths of 14 meters, their eyes as large as dinner plates to capture every photon of bioluminescent light. Why do they grow so large? The prevailing theory involves a combination of factors. Extreme cold slows metabolism, allowing animals to invest more energy in growth. Scarce food favors larger bodies that can fast for longer periods, and fewer predators means less evolutionary pressure to stay small and nimble. But here's the catch, quite literally. These giants are slow-growing and long-lived. Some deep-sea fish can live for centuries. Cold water corals might persist for thousands of years, their colonies expanding at rates measured in millimeters per decade. When you've invested decades or centuries growing to adult size, you need environmental stability. You need time. And time is precisely what climate change isn't giving them. Warming waters are hitting the oldest, slowest-growing species the hardest, wiping out individuals that were alive when humans were still figuring out agriculture. Let's descend deeper into the horror of adaptation gone wrong. Many abyssal creatures have evolved transparent or ultra-black skin, the former to avoid casting shadows in bioluminescent light, the latter to absorb light so completely they become invisible even when illuminated. Some have evolved antifreeze proteins in their blood to survive near-freezing temperatures. Others have lost their eyes entirely, since vision is useless in absolute darkness, reallocating those metabolic resources to enhanced smell or pressure-sensitive lateral lines. There are fish whose bones are cartilage because calcium is hard to come by in the deep, making them flexible enough to withstand pressure that would pulverize surface creatures. Every single one of these adaptations represents millions of years of trial and error, countless generations of selection pressure refining survival strategies down to the molecular level. And now the environment they were perfected for is disappearing. It's like spending your entire life training to run a specific race only to show up and discover the track has been replaced with an obstacle course. Except these creatures don't have a lifetime to retrain. They have, at best, a few generations before their populations collapse. Here's where mystery merges with adaptation in ways that should unsettle you. Approximately 90% of creatures between 200 and 1,000 meters depth are bioluminescent. Think about that. 9 out of 10 animals in the twilight zone produce their own light through chemical reactions, bacterial symbionts, or specialized organs. They use light to hunt, to communicate, to attract mates, to confuse predators, to camouflage themselves against the faint glow filtering from above. The deep ocean isn't actually dark. It's an alien disco of blues, greens, and reds pulsing and flickering in patterns we're only beginning to decode. But as ecosystems destabilize and species migrate, these light signals are getting scrambled. Predators following familiar bioluminescent patterns find themselves chasing extinct prey. Species that evolved specific flash patterns to identify potential mates are encountering strangers from different regions, their languages of light mutually incomprehensible. Some researchers have documented unexplained mass bioluminescent displays, synchronized light shows involving thousands of creatures with no apparent purpose. Are they panicking, trying to communicate across fragmenting populations, signaling distress in a language we cannot understand? We simply don't know, and that uncertainty is perhaps the most unsettling aspect of all. Now consider the deep-sea corals, ecosystem engineers that create habitats for thousands of other species. Unlike their shallow water cousins that host photosynthetic algae, deep-water corals must capture all their food from passing currents. They grow with agonizing slowness. Some cold-water coral reefs are estimated to be over 8,000 years old, predating the pyramids of Egypt. These ancient structures provide critical habitat, nursery grounds for fish, shelter for invertebrates, feeding stations for everything from sea stars to octopi. But coral skeletons are made of calcium carbonate, and as the ocean absorbs carbon dioxide, it becomes more acidic, literally dissolving the chemical foundation these organisms need to build. Combine that with warming waters, even 1/10 of a degree per decade can stress corals adapted to stable cold, and you're looking at ecosystems that survived ice ages now facing collapse within a human lifetime. When these reefs die, they take with them the entire community of life they support. It's not just the loss of a species. It's the unraveling of an entire ecological tapestry woven over millennia. So what does all this adaptation and vulnerability mean for the deep ocean's future? We're witnessing natural selection in fast forward, but evolution requires variation, time, and survival. Many deep-sea species have small populations, slow reproductive rates, and limited genetic diversity, precisely the opposite of what you need to evolve quickly. Some species might adapt. The opportunistic ones, the generalists, the fast reproducers could potentially adjust to new conditions. But the specialists, the giants, the ancient corals, the perfectly calibrated predators, they're living on borrowed time. We're losing biodiversity we never even cataloged, species going extinct before science learns their names. And here's the final horror. These creatures aren't just passive victims of climate change. They're active players in regulating Earth's climate, sequestering carbon, cycling nutrients, maintaining the ocean's capacity to absorb heat and CO2. As they disappear, the ocean's climate regulation weakens, accelerating the very changes that are killing them. It's a feedback loop of loss. Adaptation becomes maladaptation, survival strategies become death traps, and the monsters of the deep, shaped by necessity into perfect beings for their world, find that world no longer exists. What rises to replace them remains a mystery written in darkness, a future we can neither predict nor prevent. Imagine sailing through the Indian Ocean on a moonless night when suddenly, the sea around you begins to glow, not with scattered sparkles like disturbed plankton, but with a steady, milky luminescence that stretches to the horizon in every direction. The water glows pale blue-white, bright enough to read by, turning the ocean's surface into a ghostly mirror of the sky above. Sailors have reported these milky sea events for centuries, describing them with equal parts wonder and dread. Vast stretches of glowing ocean visible from space, sometimes covering areas larger than entire countries. Scientists now believe these phenomena are caused by massive blooms of bioluminescent bacteria, possibly triggered by warming waters that create ideal conditions for their explosive growth. But here's what should unsettle you. These events are increasing in frequency, appearing in regions where they were rarely documented before. The ocean is lighting up, and we're not entirely sure why. Is it a natural response to changing conditions or something closer to a distress signal, a planetary SOS written in living light that we're only beginning to learn how to read? Let's descend below the surface, into the twilight zone where bioluminescence isn't rare. It's the norm. Between 200 and 1,000 meters depth, approximately 90% of creatures produce their own light. Think about that staggering statistic for a moment. In this realm of perpetual dusk, where the last rays of sunlight fade to nothing, almost every living thing has evolved the ability to create light through chemical reactions or bacterial partnerships. Anglerfish dangle glowing lures to attract prey. Lanternfish have rows of photophores along their bellies that help them blend into the faint light filtering from above, a camouflage technique called counter-illumination. Vampire squid flash bioluminescent clouds to confuse predators. Hatchetfish use light to communicate with potential mates. It's an alien world of living lanterns, pulsing and flickering in patterns refined over millions of years. Each flash, each glow, each burst of light carries meaning. A language of luminescence that coordinates hunting, mating, hiding, and warning throughout the largest habitat on Earth. But what happens when the speakers of this language start disappearing, or when environmental stress scrambles their carefully evolved signals? Here's where mystery deepens into something approaching the supernatural. Scientists have documented unexplained bioluminescent displays in warming waters, mass light shows involving thousands of organisms with no apparent purpose. These aren't the normal patterns of hunting or mating. They're synchronized events that suggest communication or perhaps collective panic. Imagine hovering in a submersible in absolute darkness when suddenly, hundreds of creatures around you begin flashing in unison, creating waves of blue-green light that ripple through the water column like some vast, alien heartbeat. Then, just as suddenly, darkness returns. Researchers have captured footage of these flashback events, as they're sometimes called, but struggle to explain them. Are organisms trying to communicate across fragmenting populations as migrations separate them from familiar groups? Are they responding to environmental stressors we can't detect with our instruments, changes in magnetic fields, subtle vibrations, chemical signals carried on currents? Or is it something more disturbing? A collective distress response? The bioluminescent equivalent of a scream echoing through the abyss? Consider the mechanics of bioluminescence itself, because understanding how it works makes its increasing occurrence even more unsettling. Most bioluminescent organisms use a chemical called luciferin that reacts with oxygen in the presence of an enzyme called luciferase, producing light with almost no heat, biological cold fire. Some creatures house symbiotic bacteria that glow continuously, using shutters or filters to control when and how their light appears. Others can trigger flash patterns as precise as Morse code, controlling the timing, intensity, and wavelength of their luminescence. This level of control requires significant metabolic investment. Creating light costs energy that's precious in the food-poor deep sea. So why are bioluminescent events increasing? If organisms are expending more energy on light production, it suggests something has fundamentally changed in their environment. Perhaps warming waters have disrupted normal communication channels, forcing creatures to signal more aggressively to find mates or coordinate group behaviors. Perhaps the stress of compound state changes, temperature, oxygen, salinity shifting simultaneously, triggers panic responses that manifest as light. We're seeing the symptoms of ecosystem distress written in bioluminescence, but we lack the lexicon to translate what we're observing. Now let's talk about a phenomenon that borders on the inexplicable: the deep scattering layer. During World War II, sonar operators detected what appeared to be a false seafloor, a dense layer that reflected sound waves, mimicking the ocean bottom but at the wrong depth. Stranger still, this phantom floor rose toward the surface at night and descended during the day. It took years to realize they discovered the largest migration on Earth. Billions of small fish, squid, and crustaceans rising each night to feed in surface waters, then retreating to the deep during daylight to avoid predators. This biomass is so immense it affects sonar readings across entire oceans. But here's the eerie part. The deep scattering layer is bioluminescent, glowing with the combined light of countless organisms. As it rises and falls, it creates waves of living light sweeping through the ocean's midwaters. Recent studies suggest this migration is changing in response to warming, shifting to different depths, altering its timing, perhaps even fragmenting in some regions. When the largest coordinated biological event on the planet starts changing its rhythm, what does that mean for the countless species that depend on it? And what are we to make of reports describing the layer glowing more intensely than in past decades? There's a particular species of jellyfish, Attala wavillii, that deserves special mention in any discussion of deep-sea bioluminescence and mystery. When attacked by predators, this jellyfish doesn't just flee or fight. It produces a spectacular bioluminescent display called a burglar alarm. Waves of blue light pulse across its bell, radiating outward in concentric circles that can be seen from remarkable distances in the dark water. The purpose? To attract even larger predators that might eat whatever is attacking the jellyfish. It's essentially calling for help by advertising the presence of a meal. But scientists diving in warming waters have reported Attala producing these displays unprovoked, flashing their burglar alarms with no visible predators nearby. Are they responding to stress? To temperature changes their bodies interpret as danger? Some researchers have speculated that as ecosystems destabilize, organisms accustomed to stable conditions might be experiencing something like sensory overload, their threat detection systems triggering false alarms in response to environmental changes they haven't evolved to recognize as benign. Or perhaps the alarms aren't false. Perhaps these jellyfish are detecting threats we can't measure yet. Chemical changes, pressure anomalies, vibrations from collapsing ecosystems reverberating through the water. And then there are the milky seas themselves, which deserve deeper examination because they represent bioluminescence at a scale that defies comprehension. Satellite data has confirmed events covering over 15,000 square kilometers, an area roughly the size of Connecticut, glowing continuously for hours or even days. The leading theory attributes these to Vibrio harveyi, a bioluminescent bacterium that forms massive blooms when conditions align perfectly. But why now? Why more frequently? Why in new locations? Warming waters create stratification, layers of different temperature and density that can trap nutrients near the surface, fueling bacterial blooms. Climate change is also altering ocean currents and upwelling patterns, potentially bringing nutrient-rich deep water to the surface in unexpected places and times. So milky seas might be an indirect consequence of warming. Changed circulation patterns creating perfect conditions for bacterial explosions that turn the ocean into a ghost light. Yet even this explanation feels incomplete. Sailors describe the experience as profoundly unnerving. Being surrounded by glowing water with no visible source, no way to explain it, the boat seemingly suspended in luminous fog. It's beautiful and wrong at the same time, a sign that the ocean's normal rules have been suspended. So what verdict can we draw from these ghost lights and milky seas, from unexplained bioluminescent displays and changing migration patterns? The deep ocean is broadcasting information constantly, using light as its primary language in a realm where sound travels for miles but photons die within meters. We're seeing an increase in this bioluminescent chatter, but we lack the context to understand most of what's being said. Are we witnessing panic, adaptation, communication across fragmenting populations trying to maintain contact as migrations pull them apart? Or are we simply seeing more bioluminescence because we're finally deploying more submersibles and cameras into regions we've historically ignored? The truth is probably some combination of all these factors, but the uncertainty itself is unsettling. The deep ocean is changing in ways we can measure: temperature, salinity, oxygen, and in ways we can see but not yet interpret. Every unexplained light show, every milky sea, every synchronized flash might be a clue to transformations happening faster than we can study them. The abyss is speaking in tongues of light, telling us something urgent about its distress, its adaptation, its transformation. And we're still learning the alphabet of this luminous language, racing to translate messages that might be warnings, farewells, or something we don't yet have words to describe. Beneath the seafloor, buried under sediment and pressure, lies something that shouldn't exist by the laws of everyday physics. Imagine ice that burns. Frozen water laced with methane gas, stable only under crushing pressure and near-freezing temperatures, a substance so paradoxical scientists call it fire ice. These are methane hydrates, and they represent one of the largest reservoirs of carbon on Earth, dwarfing all known conventional fossil fuel reserves combined. For millennia, they've remained locked in place, entombed in sediments along continental margins and beneath polar permafrost, held stable by the cold, dark waters above. But here's the nightmare. Those waters are warming. As heat penetrates into the deep ocean, it's reaching layers that haven't changed temperature in thousands of years, and when you warm methane hydrate even slightly, it destabilizes. The ice melts, releasing methane gas that's been trapped for eons. And methane is a greenhouse gas 86 times more potent than carbon dioxide over a 20-year period. We're not just talking about climate change anymore. We're talking about a feedback loop that could amplify warming beyond our worst projections, triggered by processes already underway in the darkness beneath our feet. Let's understand what we're dealing with here, because the science itself reads like something from a disaster novel. Methane hydrate forms when methane molecules get trapped in crystalline cages of water ice under specific conditions. High pressure and low temperature. These conditions exist along the edges of continents where the seafloor drops away into the abyss, typically at depths between 300 and several thousand meters. The deposits look like dirty ice or sometimes like exposed rock faces on the seafloor, but when you bring a sample to the surface, it fizzes and melts, releasing bubbles of flammable gas. You can literally set a chunk of it on fire, watching ice burn with a ghostly blue flame. Scientists estimate there are trillions of tons of methane locked in these deposits worldwide, more energy potential than all coal, oil, and natural gas combined. But accessing it safely is nearly impossible, and the real danger isn't extraction, it's destabilization. As ocean bottom temperatures rise even a fraction of a degree, the stability zone where hydrates can exist starts shrinking. The ice begins to melt from the edges inward, releasing gas that percolates through sediments, seeking pathways to the water above. Now here's where things get genuinely terrifying. The methane doesn't always seep out slowly. Sometimes it explodes. Geologists have discovered massive craters on the seafloor, some over 30 meters deep and hundreds of meters wide, blasted into existence when pressurized methane broke through overlying sediments in catastrophic blowouts. These pingos, as they're called, are mounds of sediment pushed upward by accumulating gas beneath, growing until the pressure becomes too great and they erupt. The Arctic Ocean alone has been identified as containing around 600 locations actively seeping methane right now, and many more pingos that could blow at any time. When a large hydrate deposit destabilizes, it can trigger submarine landslides, entire sections of continental slope collapsing as the ice that helped hold sediments together melts away. These landslides have generated tsunamis in the past. The Storegga slide 8,000 years ago, possibly triggered by hydrate destabilization at the end of the Ice Age, sent a wall of water crashing into Scotland and Norway, reshaping coastlines and wiping out settlements. We have evidence this happened, and we know the conditions that could trigger it again are developing right now. The geological record offers a glimpse into what large-scale methane release can do, and it's apocalyptic. At the end of the last ice age, as temperatures rose and ocean levels increased, hydrate deposits that had been stable for thousands of years began to melt. Researchers have found evidence of massive methane releases in sediment cores dating to this period, layers marked by distinctive chemical signatures indicating sudden, enormous influxes of carbon into the atmosphere and ocean. Some scientists link these events to rapid warming episodes that punctuated the overall deglaciation, moments when temperature spiked faster than the gradual thaw would predict. The methane releases may have acted as an accelerant, pushing the climate system past tipping points. Even more disturbing, once released, methane doesn't just disappear. In the atmosphere, it traps heat, driving further warming. In the ocean, bacteria consume it, using up oxygen in the process and creating dead zones where nothing can survive. The past shows us that methane hydrate destabilization isn't a theoretical risk. It's a documented feature of rapid climate transitions, and we're recreating the conditions that triggered it before. But the truly insidious aspect of the methane threat is how it creates feedback loops that amplify themselves. Warming water destabilizes hydrates, releasing methane. Methane in the atmosphere traps heat, causing more warming. More warming destabilizes more hydrates, releasing more methane, and the cycle accelerates. This is what scientists call a positive feedback loop. Positive not in the sense of good, but in the sense that it reinforces itself, spiraling out of control. Computer models attempting to predict future climate often struggle with methane hydrates because the exact timing and scale of releases are nearly impossible to forecast. How much warming triggers widespread destabilization? How quickly does released methane reach the atmosphere versus being absorbed or consumed by bacteria in the water? Do releases happen gradually over centuries, or in sudden catastrophic bursts? The uncertainty itself is frightening because it means there could be thresholds we don't know about, tipping points hidden in the system waiting to be crossed. And once you tip past a threshold, once a feedback loop engages, stopping it becomes exponentially harder. You can't just turn down the heat and expect everything to freeze again. The system has shifted into a new state. Recent research has documented something deeply unsettling: methane migration. Scientists studying hydrate deposits off the coast of Norway discovered that warming water has caused methane to migrate laterally through sediments for over 40 kilometers, 25 miles, from deep deposits toward shallower areas where it's less stable. Think about that. The gas isn't just seeping upward. It's spreading horizontally through the seafloor, seeking new escape routes, pressurizing sediments far from the original deposit. They found evidence of hydrate melting that migrated from the upper continental slope to the shelf edge, driven by water masses that were 2 to 3 degrees warmer than when the hydrates originally formed. 2 or 3 degrees doesn't sound like much, but in the deep sea, where temperature has remained stable for millennia, it's revolutionary. The hydrates are responding to warming that happened decades ago, heat that's only now reaching critical depths. This means that even if we stopped all warming today, destabilization would continue for years, possibly centuries, as heat already in the system works its way into the sediments. We've set processes in motion that have their own momentum now. Consider the broader context. Deep-sea ecosystems are already collapsing under the stress of compound state changes. Species are migrating at unprecedented rates. Bioluminescent displays suggest widespread distress. Now add methane releases into this picture. Gas erupting from the seafloor creates plumes of bubbles that disrupt water chemistry, lower oxygen levels, and alter salinity. Entire communities of organisms adapted to stable conditions suddenly find their habitat transformed into a chemical maelstrom. Some species might actually benefit. There are bacteria that consume methane, and in areas of active seepage, these bacteria form the base of specialized ecosystems including tubeworms, clams, and mussels that host the bacteria symbiotically. But these are niche communities, and their expansion comes at the cost of displacing everything else. Moreover, methane seeps create acidic conditions as the gas dissolves and reacts with seawater, accelerating ocean acidification locally and stressing any organism trying to build calcium carbonate shells or skeletons. The methane threat isn't just about atmospheric warming. It's about fundamentally altering the chemistry and ecology of the deep ocean, potentially creating dead zones, triggering landslides, and pushing ecosystems past the point where recovery becomes possible. So what does all this mean for our deep-sea future, and for us? Methane hydrates represent a wild card in climate projections, a factor that could accelerate warming beyond our current worst-case scenarios if large-scale destabilization occurs. We're conducting a planetary experiment, warming the ocean and waiting to see how much heat the hydrates can tolerate before they begin releasing their carbon en masse. Some estimates suggest that even modest increases in ocean temperature could destabilize enough methane to raise atmospheric concentrations significantly within this century. Others argue that most methane released underwater will be consumed by bacteria before reaching the atmosphere, limiting the impact. But even in the optimistic scenario, you're still talking about localized environmental disasters. Dead zones, acidified waters, collapsed seafloor structures. And in the pessimistic scenario, you're talking about a runaway greenhouse effect, warming that feeds on itself until the planet resembles something from our deep past, the Paleocene thermal maximum 56 million years ago, when massive carbon release drove global temperatures up by 5 or 6 degrees Celsius, fundamentally reshaping life on Earth. The fire ice is awakening beneath our oceans, and once awakened, it may be impossible to put back to sleep. We're watching the fuse burn on a bomb we buried ourselves, counting down to an explosion we can predict but cannot prevent. So here we are, standing at the edge of understanding, looking down into an abyss that's looking back. We've journeyed through the invisible apocalypse of compound state changes, witnessed the desperate migrations of creatures fleeing waters that have been their home for millions of years, examined the grotesque beauty of adaptations becoming maladaptations, deciphered ghost lights that might be distress signals, and confronted the fire ice awakening beneath the seafloor. Now comes the moment when we must face the ultimate question. What does all this mean? Not just for anglerfish and giant isopods, not just for methane hydrates and bioluminescent bacteria, but for the entire planetary system, including us. The deep ocean is Earth's largest ecosystem, covering more than 60% of the planet's surface and containing 95% of its biosphere by volume. When something this enormous transforms, nothing remains unchanged. The verdict is emerging from the darkness, written in temperature records, species distributions, chemical signatures, and ecosystem collapses. And it's telling us something we desperately don't want to hear. The deep ocean's transformation is already locked in, irreversible on human timescales, and its consequences will reshape civilization itself. Let's start with the most sobering fact. The deep ocean absorbs roughly 90% of the excess heat trapped by greenhouse gases. Think about what that means. Every degree of warming we've experienced at the surface represents a tiny fraction of the thermal energy actually entering Earth's system. The vast majority gets swallowed by the ocean, transported downward through currents and mixing, stored in waters that may not return to the surface for centuries. This isn't just a buffer. It's a debt written in heat, accumulating in places we can't easily access or measure. Recent research confirms that even if we stopped all carbon emissions today, deep water warming would continue for decades, possibly centuries, as the heat already in transit works its way into the abyss. The ocean has thermal inertia. It responds slowly but inexorably to forcing. This means every change we're documenting now, the migrations, the methane releases, the ecosystem fragmentations, these are responses to warming that happened years or decades ago. We haven't even seen the full effects of current heat yet, let alone what's coming. The ocean's verdict lags behind our actions by generations, and by the time we see the full consequences, it's far too late to prevent them. Now compound this thermal reality with the concept of state changes. Up to 40% of the ocean's upper 1,000 meters have already undergone significant shifts in at least 2 critical properties compared to just 6 decades ago. Some regions show simultaneous changes in temperature, salinity, and oxygen, compound transformations that push ecosystems beyond adaptive limits. When you change one variable, organisms might adapt. Change 2, and stress increases exponentially. Change 3 or more simultaneously, and you're looking at ecosystem collapse. Scientists have documented this pattern in the tropical and subtropical Atlantic, the North Pacific, the Arabian Sea, and the Mediterranean. Some of the ocean's most biodiverse and productive regions transforming into biological danger zones. And these changes are penetrating deeper, reaching into what was considered the stable heart of the ocean. The abyss itself is warming, acidifying, losing oxygen. There's nowhere left to hide. No refuge zone where the old rules still apply. The deep ocean is entering uncharted territory, and it's dragging every organism within it along for a journey into an unknown and potentially uninhabitable future. But here's where the horror becomes personal, where abstract ecological disaster connects directly to human survival. The ocean's ability to regulate climate and provide food is weakening. Marine species are already moving toward the poles 6 times faster than land animals, driven by warming that's disrupting fisheries worldwide. When deep-sea ecosystems destabilize, the effects ripple upward through food webs. Small fish that feed on deep-dwelling zooplankton find their prey has relocated. Larger predators that feed on those fish face starvation or must follow their food into unfamiliar waters. Commercial fishing stocks collapse or shift into jurisdictions that lack the infrastructure to harvest them sustainably. We're already seeing this. Fish populations moving hundreds of kilometers from their historical ranges, crossing international boundaries, creating conflicts over fishing rights. 3 billion people rely on seafood as their primary protein source. What happens when the ocean can no longer reliably produce that food? What happens when compound state changes eliminate the conditions necessary for spawning? When nursery grounds become uninhabitable, when migration routes pass through dead zones? Food security for half the planet depends on ocean health, and that health is deteriorating faster than our ability to adapt. Then there's the carbon cycle, the ocean's role as Earth's largest carbon sink, absorbing roughly a quarter of all the carbon dioxide we emit. This absorption happens through two mechanisms: physical dissolution of CO2 into seawater, and biological sequestration as marine organisms incorporate carbon into their bodies and eventually sink to the seafloor when they die. But both mechanisms are weakening. Warmer water holds less dissolved gas, reducing the ocean's capacity for physical absorption. Meanwhile, ecosystem disruption is undermining biological sequestration. When species go extinct or relocate, when food webs collapse, when the deep scattering layer fragments, the efficiency of the biological pump decreases. Less carbon gets transported from surface waters to deep storage. More stays in the atmosphere, driving additional warming. It's another feedback loop. Warming destabilizes ecosystems. Destabilized ecosystems sequester less carbon. Less sequestration means more atmospheric warming. And because deep-sea ecosystems take centuries or millennia to recover, if they recover at all, this isn't a problem we can fix quickly. We're degrading Earth's climate regulation system at precisely the moment we need it most, like destroying air conditioning during a heat wave. Consider the tipping points we're approaching or have already crossed. Recent research confirms that warm-water coral reefs, the first climate tipping point, have been exceeded, with widespread die-off already underway. Coral reefs support 25% of all marine species despite covering less than 1% of the ocean floor. Their loss represents catastrophic biodiversity collapse. But corals are just the beginning. The Atlantic meridional overturning circulation, which includes the Gulf Stream, shows signs of weakening. If it collapses, and some models suggest this could happen within this century, Europe's climate would dramatically cool while other regions overheat, monsoons would shift or fail, and sea levels would rise along the Atlantic coast. Antarctic ice shelves are destabilizing as warming waters reach their undersides. Methane hydrates are releasing gas that could accelerate warming beyond our worst projections. Each of these represents a threshold beyond which change becomes self-sustaining and irreversible on human timescales. And they're all connected through the ocean. Warming water that destabilizes hydrates also disrupts currents. Changing currents alter nutrient distribution, affecting ecosystems. Ecosystem collapse weakens carbon sequestration, accelerating atmospheric warming. It's a network of cascading failures, each one triggering others, amplifying through feedback loops we're still struggling to understand. Perhaps the most haunting aspect of the deep ocean's verdict is how it reveals the true timescale of what we've done. We think in terms of years or decades, election cycles, quarterly reports, human lifespans. The ocean thinks in centuries and millennia. Heat we added to the system in the 1980s is still working its way into the deep. Carbon we emitted decades ago is still acidifying waters in the abyss. The full consequences of our current emissions won't manifest for generations. This means we're living in a ghost future, experiencing the effects of past actions while simultaneously creating future effects we won't live to see. Our grandchildren will inherit an ocean transformed by decisions made before they were born, by heat added to the system when their grandparents were young. And because ocean systems respond so slowly, even aggressive action now won't prevent significant additional change. We've committed the planet to decades of continued warming, continued ecosystem disruption, continued species loss. The question isn't whether the deep ocean will transform. It's already transforming. The question is whether we can limit how extreme that transformation becomes, and whether we can maintain enough ocean function to sustain human civilization as we know it. So what is the deep ocean's verdict on us? It's unwitting architects of transformation. Perhaps it's this. We have treated the largest ecosystem on Earth as an infinite sink, a convenient dumping ground for heat and carbon, a resource to be exploited without consequence. We've conducted a planetary experiment without understanding the system we're experimenting on, without appreciating the timescales involved, without recognizing that the ocean stability was the foundation of our own survival. And now the results are coming in, emerging from the darkness in the form of collapsing ecosystems, migrating species, destabilizing methane deposits, weakening climate regulation, and vanishing food security. The deep ocean isn't separate from us. It's the life support system for this planet, regulating temperature, producing oxygen, sequestering carbon, providing food. When it transforms, we transform. When it destabilizes, our stability disappears. We've spent centuries treating the ocean as background, as scenery, as something that would always remain beyond our ability to affect. We were catastrophically wrong. The abyss is not infinite. Its capacity is not limitless. And we've pushed it past thresholds that won't be crossed back in our lifetimes, or our children's, or perhaps our grandchildren's. The deep ocean's verdict is final. We are all in this together, surface and abyss, linked by water and heat and consequence. What happens in the darkness doesn't stay in the darkness. It rises eventually, inevitable as tides, reshaping everything it touches. And we are only beginning to understand the world we've created.